This is chapter number 5, and the title of the chapter is Energy, Work, and Power. So, this diagram is showing that one person is pushing the wall. So, this is a kind of the mechanical work. And here also, the work is shown with the help of the diagram. Here, one person is pulling the box with some force, and he is displacing the box up to some distance. So this person is also doing the mechanical work. This picture is showing also some work is done on this box, and here also the work is done by this animal. No. So our main chapter starts from here. This is the formula for the work. The W equal to F multiplied by the displacement multiplied by the cosine theta. So in this diagram, one person is pulling this box up to some distance or the displacement. So he is applying some force on the box at some angle. So this is the direction of the motion. This is the direction of the motion. In this direction, the box is displaced. So basically, sometimes we are showing the displacement. Okay, sometimes we are showing the displacement by the d, or sometimes like in this formula we are showing the displacement by the del x, but both they have the same meaning. So in this formula, the F is the force applied on the box, and the del x or the delta x is the displacement here. Like from here to here, this is the displacement in the box. And this theta, this is the angle between the direction of the force and or the horizontal direction or the direction of the motion. So this is the angle theta. And the work, the unit of the work is joule. So here the maximum work is shown. See, we have this formula for the work. The W is equal to the force multiplied by the displacement multiplied by the cosine theta. So this is our normal formula. Okay, but sometimes the work is maximum and sometimes the work is minimum. So what is the condition? Okay, so what is the condition for the so here what is the condition? Okay, the rule. So what is the condition? So what is the condition for the maximum work? So the condition is it is shown in this diagram. So the person is pushing this table. So this is the table, and this is the direction of the force, and this table is displaced. Okay, so this is the direction of the displacement. So here the angle between the force and the direction of the motion or the direction of the displacement is 0 degree. So this is 0. They are parallel like this. This is the direction of the force and this is the direction of the motion or the direction of the displacement, like that. So here the angle is 0 degree. So the theta is 0 degree. And if I put this theta in cosine here, so the cosine 0 degree is 1, the plus 1. So in the cosine table, this is the maximum value of the cosine. Okay, so if it is like this, so if the person is moving the object like this or like this, okay, so in this case the person is doing a maximum work. Okay, and this is, and the value of the cosine theta is 1. So this is the formula. Okay, the W equal to F multiplied by delta X. So this is the formula for the maximum work. So in the similar way, the work is minimum also. The work is minimum or the zero sometimes, or the minimum value. Okay, so when it is minimum, actually there are two conditions. Okay, for the work to be minimum, there are two conditions. Okay, for the work to be minimum, this is the case number one. Okay, so it is case number one means like one type I can say. Okay, so when the work is minimum, so you can see in this, okay, in this diagram here, the person is lifting a box, okay, by some force, okay, lifting a box, and this person is moving in this direction. Okay, so this picture is representing, okay, like that a person is moving, okay, on the ground by holding a box like that. Okay, so here, so this is the formula for the work. Okay, the W equal to this is F and the delta X, and this is the cosine theta. So here we have to see what is the angle, what is the angle between the direction of the force and the direction of the motion. So here the angle is 90 degree. In this case the angle is 90. Okay, so here if I put this 90 in the cosine, so the cosine 90 degree is 0. Cosine 90 is 0. Okay, so if I put this cosine 90 0 here, so the work is going to be minimum and the value of the work is 0. So this is the one condition, okay, for the minimum work. So this is, okay, this is case number one. And there is a one more case. Okay, there is a one more case when the work is, okay, when the work is 0. Okay, actually in this case, okay, in the case number one, the theta here is 90. So due to theta 90, this work is 0. This is the thing here. Okay, and in the case number two, okay, in the case number two, like this is the formula for the work. Okay, the W equal to multiply by the displacement, and here this is cosine theta. Okay, this is the normal formula for the work. Now in the case number two, okay, in the case number two, in the case number two here, they are saying the object is not moving. Okay, the displacement, okay, of the object is 0. So displacement of the object is 0. What is the meaning of this? The meaning of this means if the object is at rest, okay, it is not moving. Okay, so if the object is not moving, okay, then this is 0. Okay, so here because the displacement is 0, so that's why here the work is 0. So these are the two cases. Okay, so when the work is 0 or the work is minimum. Okay, so in the case number one, this is the condition. Okay, theta is 90, and the case number two, work is 0 or the minimum, but the condition is different. Okay, so what is the different condition here? They are saying, okay, the rule says here the displacement is 0. Okay, the object is not moving. Now here there is a small problem, okay, on the formula for the work, and here they are asking, okay, how much work is done, okay, how much work is done by the boy pulling his sister 30 meter, okay, in a wagon as shown in the diagram. So this is a wagon car, okay, in which okay, one girl is sitting, and assume no friction acting on the wagon. Okay, so assume no friction, so the meaning is there is no opposite forces. Okay, no friction means there is no opposite forces. Okay, so how many forces are acting here? So we have to take the total. The meaning is like that. So here we have to find the work. Okay, so what is the value of the work, and the displacement is given. So okay, so if you find the solution of this, so what is given here? The given is the displacement. Okay, actually don't be confused. Okay, sometimes as I told you, okay, sometimes the displacement is shown by the letter D, and sometimes the displacement in some books it is shown by letter S, and sometimes it is shown by the delta X. Okay, both are okay. Okay, all are okay. So these are the common, okay, the letters, okay, used to represent the displacement. Okay, so here the displacement is given how much. It is given 30 meter. Okay, and the force, it is shown in the diagram, and the force is, okay, and the force is 50 newton. This is given. And yeah, so the angle, okay, so angle with the force and the horizontal direction is 30 degree. So here the theta is given, that is 30 degree. Okay, so they are saying what is, so what is the value of the work. So we have to find what is the value of the, okay, what is the value of the work. Okay, so we have to use the rule. Okay, we have to use the formula. And the formula for the, okay, and the formula for the work is, okay, the formula for the work is, uh, the formula for the work is the W is equal to the force multiply by the displacement and multiply by the cosine theta. Okay, so this is there. So I have to feed, okay, the value of the force, which is 50 newton, and the value of the displacement is 30 meter. It should be meter, okay, not centimeter, and not millimeter, not kilometer, okay, only meter. The displacement should be only in the unit of the meter. And here this is the cosine theta, and the value of the theta is 30 degree. Okay, so if I solve from my calculator, okay, so I calculated the answer of this, okay, uh, equation. It will be 1299. So this is 1299, and the joule. Okay, the unit of the work is joule. Okay, so this is our answer here. Okay, for this, for the question number 1. Now this is the question number 2. This is on the same idea. Okay, but here they are asking something different. Okay, to evaluate, okay, to find. Now here a person pushes a lawn mower. Okay, so this is a lawn mower here. Okay, this is the lawn mower with a constant force of 75 newton. So this is the value of the force. Okay, 75 newton. This is the value of the force over a distance of 25 meter on a level ground. So this is equal to the displacement. Okay, and if the work done on the mover is 1.4 kilojoule, so the work done by the person, okay, on the work done by the person on the mover is 1.4 kilojoule. So this value is given for the work. Now they're asking what is the angle. Okay, now they're asking what is the angle between the applied force. Okay, so this is the direction of the force between the applied force and the horizontal direction. Okay, horizontal direction or the direction of the motion. Okay, so this is the horizontal direction. Okay, or this is the, okay, or this is the direction of the motion, and this is the direction of the force. So this angle we need to find according to the question. Now here I am writing, okay, what it is given. Okay, in the question, the value of the force is given, that is 75 newton, and the value of the displacement, it is given 25 meter, and the value of the work done is given, this is 1.4 kilojoule. Okay, so this is kilojoule, and the unit of the work is joule, not a kil. This we have to, okay, eliminate. We have to keep the value for the kilo. And in terms of okay, the joule, the value would be 1.4. Then I need to multiply by 10 to the power 3, okay, and make it in the unit of the joule. So this value we have to use, and this is the, okay, work value given. And what we have to find. Now we have to find the angle here. We have to find the value of the angle, okay, between the force and the displacement or the horizontal direction. Now okay, so we have to use the formula for the, okay, we have to use the formula for the work, and the formula for the work is the W is equal to the F multiply by the displacement and multiply by the cosine theta. Actually here I need to find this. Okay, so what I will do to make it simple, okay, to make mathematically simple, I will take this factor outside. Okay, so if I take this cosine theta, okay, extreme left side, so what it will come, okay, so this will be here only, and this will go to the other side. Okay, this is multiply here. Okay, so when I will change the side of this, it will go in the it will go in the division there. So this will be the work and divided by the force and then the displacement. Okay, so this rule we have to use for our problem here. Now, okay, so now I am writing this rule here. Okay, so this is the cosine. Okay, so this is the cosine theta, and this is equal to the work, and this is the force and the displacement. So the value of the work, the value of the work is this is 1.4 multiplied by 10 to the power 3. Okay, kilojoule you have to always you have to change. Maybe if it is megajoule, you have to change. Okay, if it is for example nanojoule, megajoule, gigajoule, okay, so this you have to change to joule all the time. And the value of the force, okay, it is given here. Force how much? Okay, so the value of the force is 75. So the value of the force is 75, then multiply by the displacement value, and the displacement value is 25 meter. So if I do the calculation of the whole part, okay, so if I calculate this and if I calculate this, so I am getting the answer. Okay, here this will be 0.74. Okay, and this is the value of the cosine theta, not theta. The question is asking what is the value of this. So how to find the value of the theta? Okay, so I'll change the side of this cosine. Okay, so I will keep the theta here and cosine will go to the other side. Okay, and I will keep the cosine here, but this will come with the inverse. Okay, when it will change the side, it will come with the inverse. And here I will put the value. Okay, this is 0.75, and if I calculate, okay, in the calculator, okay, so if I calculate in my calculator, okay, so how much I am getting? I am getting the value, okay, of this is 41. Okay, this is 41.6 degrees. Okay, so this is your, okay, so this is your answer. The angle between, so this is, okay, so this angle is 41.6 degree. So this is our answer. Okay, so the question number 3 is already solved here. Okay, so you can try at home. This is easy. Okay, so this is also, this question is solved, question number 4. Okay, this also you can try at home. This also the same idea. Okay, nothing different from the last, okay, the two problems I solved. This is also the same idea. Okay, now we are moving to the other topic. Okay, the energy. Okay, basically, okay, so one thing I want to tell, that the energy and the work, they have the same meaning. There is no difference between, if I say, okay, so if I write something, okay, for the, okay, for any formula, okay, for example, the work, okay, the work and the work, okay, the energy and the work both have the same meaning. Basically, technically, both have the same meaning. Okay, for example, okay, for example, if I write the formula for the work, okay, like this is the W equal to, okay, the force and the displacement, and this is the cosine theta. So this is the work basically. Okay, I told you. But if I write here, this is the formula for the energy, there is no harm. This is okay, technically it is okay. Okay, so here it is explained like how many types of the energies are there. So there are so many types of the energies, okay. And the sound, okay, the sound energy, heat energy, and the light energy, nuclear, and the kinetic energy. So there are so many types of the energies are there, and which are most common, okay. So it is displayed here. Okay, so here the first line is the energy is the ability to do the work. So the energy, okay, is same like work. Okay, so as I told you, okay, on the last line, this is the definition of the energy. Okay, energy is the ability to do the work. So the main thing is this is basically this line. Okay, so if it comes in the examination, okay, so you have to write this is the definition of the this is the definition of the energy. Okay, if this is coming, so the same you have to write. As here, okay, so different types of the forms of the energy given here. Okay, this is like mechanical energy, okay, electrical, and the heat, the light, the sound, chemical, nuclear. There are so many. And okay, so here they are saying okay something about the actually mechanical energy. So we have to study okay in this chapter mechanical energy in detail. This is a mechanical energy. So what is the rule for the mechanical energy? Basically the mechanical energy, okay, the mechanical energy is the sum of, okay, is the sum of the kinetic energy and the potential energy. This is the rule. Okay, so the mechanical energy is the sum of kinetic plus potential. Okay, so here okay, so here too much information is given, okay, up for the kinetic energy, and I am okay writing in a very brief way, okay, for the rule for the kinetic energy. So there are one rule, okay, for the kinetic energy, and I'm writing here. Okay, so the one rule is about the about the kinetic energy. Okay, the kinetic energy is equal to the half the mass and the velocity square. Okay, so this is the formula for the kinetic energy. Okay, after that there is a one more rule given. Okay, that rule is basically for the work. Okay, basically this rule is for the work. Okay, so this rule is for the work, and actually here there is a relation between the work and the energy. Okay, so what it is stated there, the work is equal to, okay, the work is equal to the change, this is a change, the delta is a change in the kinetic energy. Okay, this is a work, this is a rule. Okay, now if I open this delta, okay, then I can do like this. Okay, this is the kinetic energy final minus the kinetic energy initial. Okay, so this is the difference between the two kinetic energies, the final and the initial. Okay, now what I am going to do, I'm writing okay this rule, okay, here, and this rule here. And I will use this final and the initial. Okay, so here, so for the okay, so for the kinetic energy final, I'm writing the rule. So this is half the mass and the velocity square, but this velocity is this one final. Okay, so I'm writing here final, and the minus half mass and the velocity square, but this velocity is initial. Okay, so this is the rule, okay, for the work done, okay, for the work. And if I, okay, so if I take okay, if I make this rule simple, so what I can do, I can take this, okay, common from here. So this is half m coming here, and this half m is coming here. So what I can do, I can take this, okay, I can take this common here. Okay, easy to solve. Then this would be okay the half the mass, and in the bracket this is the velocity final square, and minus the initial velocity, okay, square, and this is equal to the work done. Okay, so this is the new formula. okay, for the work done. This is the formula for the kinetic energy, and this is, okay, I can say the rule number 2, okay, for the kinetic relation between the kinetic energy and the work done. Okay, so this is a already solved one example here. Okay, you can, this is simple. Okay, just here they're asking, okay, what is the velocity of the okay, of what, of the molecule. Okay, so this I am doing. This is little bit not very easy. Okay, so the question number 8 is, there is a 30-gram bullet initially traveling at 500 meter per second, penetrates 12 centimeter into the wooden block. What is the force does it exert? Okay, so they are talking about this bullet. Okay, so they're talking about this bullet, this one. Okay, so this bullet has the mass, okay, the mass of 30 gram, but gram I cannot use. Okay, the mass of the 30 gram, and the velocity of this is given by this is 500, okay, meter per second, and this bullet penetrates, okay, this is a wooden block, and it penetrates 12 centimeter in the wooden block. So like from here to, like from here to here, like from here to here, okay, this is the, I can say, this is the displacement here, okay, according to our, you know, our formulas, okay, our parameters. So here this is the displacement, okay, this is the 12 centimeter here. So this bullet, okay, is, okay, this bullet is hitting, okay, this bullet is hitting here, okay, this bullet is hitting here, okay, hitting here with this velocity. So they're asking, okay, so they're asking what is the value of the force. Now they're asking what is the value of the force, okay, that this bullet is hitting here, okay, here hitting. So we need to find the force. So okay, so for this question, what given to us, okay, what parameters, okay, what are the parameters that are given to us. Okay, so actually we have to find the force here. So what are the parameter given? The value of the mass, okay, the value of the mass is given, that is 30 gram, okay, but gram we cannot take. So I need to multiply by, okay, I need to multiply by 10 to the power minus 3, and this will convert to the kilogram. Now this is the velocity of the bullet, okay, and this is 500 meter over second, and there is a displacement, okay, that the bullet is crossing, you know, this area, okay, of the wood, and this is equal to 12 centimeter, okay, but 12 centimeter I cannot take, so I need to change to the meter. So this would be, okay, the 12 multiplied by 10 to the power minus 2, and this will be converted to the meter. Okay, now I know the mass given and the velocity given, so I can find, okay, something about you know, something about the kinetic energy. Okay, some idea is coming. Okay, so what I have, okay, given here, okay, so it seems that I can find easily the kinetic energy, but there is no, you know, there is no formula, okay, for the kinetic energy which is having a force. Okay, so what I can, so here what I can do, okay, so I know that, okay, I know, okay, I know that the work is equal to, okay, the work is equal to the change in the kinetic energy. Okay, this I know, and this is the rule. Okay, the work is equal to the change in the kinetic energy, but here actually only one velocity given. Okay, so normally we are using, okay, this change when there are two velocities given. Okay, but in this type of the question there is only one velocity value. Okay, so what I can do, I can modify this rule. Okay, I can modify this rule. Okay, according to our condition that the work is equal to, not change. I'm not taking the change. Okay, so the work is equal to the kinetic energy. This I am taking the rule here. Okay, the work is equal to the kinetic energy, not the change. Change we are using when we have the two. Okay, the initial and the final. But here I have only one, so I'm making it simple and removing this the delta. Okay, so here if I put the formula, okay, for the kinetic energy, so this is the half and the mass and the velocity square. I have the mass, I have the velocity. So what I will do first, I will find the value of this. Okay, so this is the half and the mass of the, okay, bullet. How much? The mass of the bullet is 30. Okay, this one. Okay, 30 multiplied by 10 to the power minus 3. So this is 30. Okay, 10 to the power minus 3. Now the velocity of the bullet. Okay, so what is the velocity of the bullet? The velocity of the bullet is 500 meter over second. So this value, okay, I need to put at the place of the v. So v, and this is the 500 meter over second, and then the power 2. Okay, so if I solve the value for, okay, so how much, if I'm solving, okay, in my calculator, so how much the answer will come? So the answer will come here. This will be, 3750. This number will come. Okay, joule. So this number I got by using the value of the by using the formula of this kinetic energy from this idea. Okay, but they are asking, I need to find the force. Okay, so this is, I know this is equal to work, and I know, okay, and I know the work is, okay, the work is equal to the force multiplied by the displacement, and this is the cosine theta. Okay, so this I know. If I find here, if I find the work from this rule, here I have the value of the force. No, the force. Okay, so here we need to find the force. Okay, so okay, so we need to find the force. Okay, so what I will do. Okay, so I have the value of the work or the value of the kinetic energy. Okay, this number. So what I will do, this I will keep here. Okay, so at the place of the work. So I'm keeping here the force multiplied by the displacement, and this is the cosine theta, and this is equal to 3750. And here I need to find the value of the force. Okay, so the force is equal to, this is the 3750, and divided by, this will go other side. Okay, the delta x and the cosine theta. So this is the delta x and multiply by the cosine theta. Okay, so what is the value of the theta? So we need to check the direction of the force and the direction of the displacement of the bullet. Okay, so if I go back to the figure, okay, so if I go back to the figure, now this is a bullet. Okay, and this is the direction of the displacement. Okay, this is moving in like in this direction. Okay, and here this is hitting, okay, to the wooden surface here. So this is the direction of the force. So here the direction of the force and the direction of the displacement, they are parallel. Okay, so they have the angle of 0. So here I will keep the value, okay, 0 degree. So this is 3750, and the displacement value is how much? That is the 12 centimeter. Okay, or this value in meter. So this is the 12 multiplied by 10 to the power minus 2 meter, and this is the cosine 0 degree. The value of the angle is 0. So the force is equal to, okay, so if I calculate from my calculator, so how much it will come. Okay, so this will come approximately 31,000. Okay, so this is 31,250 Newton. So this is the answer for the force. And here this is the problem. So question number 9. The question number 9 is a 6 kilogram block starting from rest. Okay, so this is the, okay, so this is the box here, okay, in this diagram, and the box is starting from rest. Okay, so this is the rest position of the box. A 6 kilogram box starting from rest is pulled to the right side. Okay, is pulled to the right side. So this is the right side. This side is pulled to the right side on a frictionless horizontal surface by a constant force of 12 Newton. So this is the force applied on the box, and the value is given, that is 12 Newton. And determine the block's velocity after it has traveled 3 meter horizontally. So the box started from here and the box shifted up to here. Okay, so they are saying, they are saying this box has traveled the 3 meter distance, okay, or the displacement. So they are saying what is the velocity of the box. Okay, what is the velocity of the box after it has traveled this 3 meter. Okay, so we have to find the velocity here. Okay, so how to do this problem? Okay, so what it is, given here. So what it is given here, so I'm writing, okay, the given parameters, okay, for this thing. It is given, okay, so they are saying this started from rest. So the meaning is the velocity, the initial velocity, okay, of the box is 0 meter over second. So here the value of the vi is given, that is 0 meter over second, and they are saying the mass, okay, the mass of the box is 60 kilogram, and also they are saying the force applied on the box is 12 Newton. So the force here is 12 Newton. Any other thing? Yeah. So the displacement also given, and this is 3 meter. Okay, so the value of the displacement also given, and this is 3 meter. And what we have to find, we have to find, okay, so here we have to find the velocity. Okay, actually this velocity we have to find at the end of this 3 meter. So we have to find what is the value of the vf. So we have to find what is the value of the vf. This is the question here. Okay, this is the question. So here they have given some, okay, the force and the initial velocity and the mass, something like this. Okay, so I can try, okay, so I can try the formula. Okay, I can try the formula, relation between the work, okay, the relation between the work and this half mass, and in the bracket this is the vf square and this is the vi square. Okay, so I need to find this. Okay, so I need to find here this. I have the value of the mass. Okay, I have the value of the vi. Okay, so but I don't have the value of the work. Okay, so this also I need to find. Okay, so I will use my old formula, okay, for the work. I know, okay, the other rule, okay, for the work, and that rule, okay, for the work is, okay, for the work is the force multiply by the displacement and multiply by the cosine theta. Okay, so this is my old rule. So by using this rule, okay, I can find the value of the work here. Okay, so let us put all the values here, and the value of the force given, this is 12, and the value of the displacement is 3 meter, and the cosine theta is 0. Okay, why it is 0? Because this is the direction of the force, and this is the direction of the displacement. See, this is the direction of the displacement. Okay, the box is moving in this direction, so the angle between this arrow and this arrow is, they are parallel. Okay, so here the value of the theta is 0 degree. Okay, so I will put here 0 degree. Okay, then I will find the answer. Okay, how much answer is coming, let me calculate. Okay, so the cosine 0 is 1, and this will be, okay, so this will be 36 joule. So by using this rule, the value of the work is coming 36 joule. So what I will do now, okay, so what I will do now here, I will put this work value, okay, 36, okay, in this equation here. Okay, so if I say this is the equation number 1, so in this equation I will put the value of the, okay, work, that is 36 joule. So if I now here, this is the work and the half and the mass, and this is the v square, vf square minus the vi square, and this is coming 36 and equal to, okay, 1 by 2, and the mass of the box is how much? The mass of the box is 60 degree, is 60 kilogram. Okay, it is 60 kilogram, and the value of the vf we have to find. Okay, so this we have to find, and the value of the vi is 0. Okay, the power 2. Now I need to, okay, so this I will take other side. So this will be 36 multiplied by 2, and this 60 will come down, okay, here, and this is equal to vf square. Okay, so if I solve everything here, so it will be how much? This will be how much? Okay, so if I solve this one, so this will come 1.2 equal to, this is vf square. So here we need the value, here we need the value of the vf, not the vf square. Okay, so the vf is equal to under root, and this is 1.2. Okay, so if I keep the 1.2, okay, in the under root, so this will be 1.0. Okay, this is 1.09, this is meter over second. Okay, so this is the value of the final velocity. This is the value of the final velocity at the end of the displacement. So this is the answer here. In the chapter number 5, in the part 2, the next topic is gravitational potential energy. So this is denoted by U, or sometimes this is denoted by the PE. Okay, the symbol is U or the PE, the potential energy or the U, and the unit of this is joule, because this is the energy. And basically this potential energy depends on the height. So the formula for the gravitational potential energy is the mass of the object in kilogram, and this is the acceleration due to gravity, and this it has a fixed value 9.8, and this is the height from the ground, like in this example. Okay, like this is the object here on the top of the building, so this has some height from here to here, so this is the height, like that. Now, on the potential energy, there is a small problem. Question number 3: if a man lifts 20 kilogram bucket from the from a well and does a 6 kilojoule of the work, then how deep is the well? So the question says a man is lifting this bucket and the mass of the bucket is 20 kilogram, and this person is doing a work of 6 kilojoule. 6 kilojoule work has been done by the person, and here they're asking like what is the height. Okay, the height of the well from the ground is like this is the ground and the bucket is here, and after some time the bucket will come up to here, and this amount of the work is done. So here what it is given to us, so I will collect the data. Here the mass of the bucket given, that is 20 kg. This is the mass of the bucket and the work done is 6 kilojoule. Okay, now the mass, okay, and the work is 6 kilojoule, and the work should be in joule, not in kilojoule. So this is 6000 joule. So here we can use the formula for the potential energy, the formula for the potential energy, that is the U equal to mg and h. And here we have to find the height. Like what is the height? What is the height of the well? So okay, so if I change the formula in the right order, so this will be the H equal to the potential energy divided by the M and the G. So this form of the formula we have to use to find the value of the height. And if I write here, okay, so we have to find the height, and this is the potential energy U, and divided by the M and the G, and the and the energy is 6000 joule, and the mass of the bucket is how much? The mass of the bucket is 20 kilogram. The mass of the bucket is 20 kilogram. Sorry, 20 kilogram, and the value of the G is 9.8. So if I calculate this, so it would be approximately 30.6. So this is 30.6 meter. This is the value of the height of the well. So the answer is 30.6 meter. And this is the law of conservation of energy. Okay, so in the part 1 I told the mechanical energy is the sum of kinetic energy and the potential energy. If I write the mechanical energy, this is the sum of the kinetic energy plus, okay, sometimes we are using like this, okay, potential energy, or sometimes we can, okay, show like that, okay, the kinetic energy and plus this is the potential energy. So this is equal to the mechanical energy. This is the rule, okay, for the mechanical energy. So this is the sum of the kinetic energy and the potential energy. And what is the meaning of the law of conservation of energy? Okay, conservation, the meaning of the conservation means the same. Okay, the meaning of the conservation means same. Okay, same, or you can say, okay, this is constant. Okay, a thing which is not changing. This is the meaning. Okay, so the meaning is this factor is always same. Okay, in any problem. Okay, in any situation, mechanical situation. So this is always constant. So this is the law of conservation of energy. Okay, this is always constant. Here some information is given. Okay, little information is given about the kinetic energy and the potential energy by taking one example. So this is the example here. Okay, now consider an object falling down. Okay, for example, this is the object and the object is falling down. Okay, by taking like this example. So the rule is when the object is at the top, when the object is at the top, so this is the top position, okay, of the object. So here the velocity of the object is always zero at this point, at the top, at extreme top point, like here the velocity is, this is a rule, okay, the velocity is zero. And if the velocity is zero, okay, so we know the kinetic energy is equal to the half mass and the v power 2. Okay, so if the velocity is zero, then the kinetic energy is zero, like this. Okay, so at the top, okay, so at the top the kinetic energy is always zero. Okay, so here the kinetic energy is always zero, but here at this point the same, at this point here the potential energy, this is potential. Okay, but the potential energy, this potential u, okay, u, or I can write like this. Okay, the potential energy at the top, okay, this is not zero. Here at this point, this is a maximum number, maximum here, this is maximum here. And when it will come like at the bottom here, so this is reverse. Okay, at like this is the bottom point. So at the bottom point, what information I have given, okay, at the top, so this is reverse. Okay, reverse means here I am saying, okay, so at the top I am saying the kinetic energy is zero, but here, okay, at the bottom this will be reverse. Okay, meaning is the kinetic energy is maximum at the bottom point here. Okay, and the potential energy is zero. Okay, at the top this is maximum. Okay, so at the top potential energy is maximum, but at the bottom it is zero. Okay, so it will be reverse. Okay, information, the property is reverse. Okay, at the top point and the bottom point, the top point and the bottom point. Okay, so here the kinetic energy is always zero. Okay, always zero at this top point, and the potential energy is maximum. And at this bottom point, okay, at this the bottom point, what information, okay, what information I have written here. So this is a reverse. Reverse means which is zero, okay, that will be maximum, and which is maximum, that will be zero. Okay, opposite. Now okay, so here one problem is given, and this problem is basically it is demonstrating, okay, law of conservation of energy. Okay, so basically this is telling the total energy is always constant by this example. So what they are saying here, question number 14, a stone of the mass, this is the mass of the stone. Okay, so this is the stone here, okay, which is the person is holding, and this is the mass of the stone, 1.5 kilogram, is released from rest. Okay, so here the velocity is zero. Okay, released from rest from a height of 9 meter. Okay, so from here to here this height is 9 meter, they are saying like this, the 9 meter, and so. Okay, and here this is the table given, and the given, okay, the given height and the speed at each position, calculate the kinetic energy. and the potential energy and the total mechanical energy. Okay, so they have given here some data. Okay, so when the height, okay, when the height is 9 meter, so the velocity is 0. So by using this formula, the ke equal to half mv square, you have to find the kinetic energy. So since the velocity is 0, so that's why it is 0. Okay, now here, this is the formula for the gravitational potential energy. So you have to put the value of the mass, then the value of the g, 9.8, and the height. Here, the height is 9 meter. Okay, so this answer will come, and this, the mechanical energy is equal to the sum of the kinetic energy and the potential energy. So this value, okay, so this plus, okay, this will come. Now we are going to some other point. Okay, little bit maybe at this point. Okay, some data we are collecting. Okay, for the kinetic energy and for the potential energy and for the total. So at the height, okay, so at the height, when the height is 7 meter, it is given the velocity, the velocity here is 6.26 meter per second. So this two information is given. So by using the kinetic energy formula, okay, this formula, and the mass you have to keep, and then the velocity you have to keep. So this answer will come. Okay, 29.4 joule. This is the kinetic energy when the height is 7 meter. Okay, like that, and the velocity given. And by using, okay, the potential energy formula mgh, and the h here is 7 meter, so this number will come. And for the total, okay, for the total you have to make the sum of this. Okay, like this 29, and okay, and this number, so this number will come, this answer will come. Now they are saying, okay, what is the ke and the u and the total at the height 5 meter, and when the velocity is 8.86, and this you can calculate, this you can calculate. Okay, and the total you are getting. And also, okay, so once it is reaching to the ground, 0 meter, the height is 0 meter, and the velocity is, okay, this 13.3. So this is the value of the ke, this is the value of the u, okay, potential energy, and this is the total. Now you can see, okay, so the rule says, okay, the rule says this energy, okay, this energy is always conserved. This energy, okay, this energy is always conserved. Okay, conserved means it is constant. Okay, this energy is, this energy is not going to change. Okay, this value, okay, is constant. This value, if you see the value here, all the values are constant. Okay, so the energy is conserved. Okay, because it is following the law of conservation of energy. Okay, so this is the example which is showing the energy in one system is conserved. Okay, it is not changing, it is same. Okay, so here the question number 15. A child slides down a playground slide if the slide is 3 meter high. Okay, so this is the height of the, okay, this is the height of, this is the slide. Okay, this is the slide, and the child is coming down, okay, from the slide, and okay, 3 meter high, and the mass of the child is 20 kilogram. So the mass of the child is 20 kilogram, and then they are asking how much. Okay, so this we have to find, how much potential energy does the child have at the top of the slide, at the top of the slide. So this is the part 1 question, like how much potential energy this u does the child have at the top of the slide. So this is the top of the slide. So here, what is the value of the u? What is the value of the potential? If I write like this, what is the value of the potential energy at the top of the slide? This is, okay, the part 1, and also they are asking the part 2. This is the second part of the question. As he slides down, okay, so he is sliding down, and he is coming like up to here. This is This is the ground. Now as he slides down, what will be his speed as he reaches to the ground? So once this child is coming here, once this child is coming here, so what is the velocity of this child? So we have to find two things here. The one we have to find, so what it is given to us. Okay, so this is the height. The height is given to us, so the height is 3 meter, and the mass of the child is how much? 20. So the mass of the child is 20 kilogram, and the value of the g we know. Okay, or it will be given in the examination. Okay, the value of the g. Now in the first part, they are asking what is the value of the potential energy u. So this is mg and h. So mgh is 20 multiplied by this is 9.8, and the height is 3 meter. So this is 3 meter. So this will be equal to, if I calculate, okay, if I calculate, so this will come 588. So this is 588 met not meter, this is joule. Okay, not meter, joule. So this is the answer for the potential energy, 588 joule. Okay, so this is the answer number, the part 1. Now in the part 2, they are asking, in the part 2 they are asking what is the velocity at, what is the value of the velocity here when the child will come, okay, to the bottom. What is the velocity here? Okay, actually here we can use, okay, the law of the conservation of energy. There is so like here I can use the key point here. Okay, the key point here is the law of conservation of energy. The law of conservation of energy. So actually I told here, okay, so the total energy is constant, that is okay, fine. Here I told you, okay, so in this example it is given, this is the total. Okay, but for the one system, okay, we can use this law like this also. Okay, sometimes, like for the one system, like how much energy, okay, so like for one system, like this is the top, okay, of the system, and this is the bottom of the system. Okay, the top and the bottom of the system. Okay, so according to, okay, so according to this information, the law of conservation of energy, whatever, okay, whatever and what type of energy, okay, whatever or what type of the energy is here, okay, is here, and in which form also. Okay, so once the system is changing, like the boy is coming from here to here, so the system is changing, so this energy is converting, okay, so this energy is converting to some other form. Okay, this energy, okay, is converting to some other form. Okay, some other form. The meaning is, okay, so what is the meaning, what is the meaning of this? The meaning of this means here, okay, so at the top, the total, okay, so at the top there is no kinetic energy because the child is not moving. Okay, so at the top, okay, so at the, okay, so at the top, purely here the energy is potential, like here. Okay, only potential. So once the child or the system is changing the position, or coming here, like here to here, okay, so at this point, okay, the other position, like in this case at the bottom side, okay, so this energy, see, energy is not going to be wasted. Okay, so the energies are changing from one one form to the other form. Okay, like that. So here Once this is coming to the bottom, so this is a potential energy. Okay, this is a potential energy, the U is a potential. So once the child is coming here, and this potential energy is changing to the kinetic energy. This is a law of conservation of the of the system. Okay, so this is changing to the kinetic energy. Okay, so basically both are same. Okay, for the system. Okay, like at the top. Okay, what the energy I have, so I have the same energy at the bottom, but the form will change. Okay, at the top I have purely, at the top I have purely the potential energy, this U, and at the bottom I have the kinetic energy. But the energy at the top and the energy at the bottom, they are same. Okay, the values are same, only here it is due to the height, and here this is due to the motion, like the kinetic energy, it is moving. Okay, something is moving. So this rule I am going to use, okay, to find the value of the velocity. Okay, so here the rule is, okay, so here the rule is, due to the conservation law. Okay, due to the conservation law. Okay, so if I say the top of the system and the bottom of the system, okay, bottom of the system, so here, okay, so here the potential energy at the top is same, like the kinetic energy at the bottom, they are same. Okay, so this is due to the law of conservation of energy. This is due to the law of conservation of energy. Okay, like what I have written here in this box. So this is due to the law of conservation of energy. Okay, so already in the part one, we found, okay, the value of the potential energy, that is 588 joule. Okay, that is 588 joule. And so this potential energy, or the U, okay, or sometimes the U. So this I'm keeping. Okay, so this I am, okay, so this I am keeping here. This is 588. Okay, and this is equal to half. Okay, half m, and this is the v square. And here, okay, the 588, and this two I will send there, okay, to the other side. And the mass of the child is 20 kilograms, so 20 kilogram I'm keeping here. And this is the v square. And so if I write this 20, okay, here, so this 20 will go, okay, this 20 will go here, and this will be, okay, so if I solve, okay, the whole part, so the v square will be, okay, the v square will be, v square I'm saying, okay, if I calculate this, so the v square, okay, the v square will be 58.8. So this is 58.8. So this is the value, okay, this is the value of the v square, and this is 58.8. Okay, but I need the v. So the v is, okay, v is, if I take the square root of, okay, so if I take the square root of this, the 58.8, and the square root of this, it will come 7.6. Okay, 7.6 meter over second. So this is the value of the, this is the value of the speed or the velocity. Okay, this is the answer, okay, for the part 2. Now this is the answer for the velocity, okay, of the child when this child will come here at extreme bottom, like when the child will come here. Now the this topic is the power. Okay, and the unit of the power, okay, the standard unit of the power is, the power is the watt. And we have, okay, we have so many rules. Okay, the four rules you can say. This is the rule number 1. Okay, this is the power equal to the work over time. And this is the rule number 2, the power equal to the kinetic energy over time. And this is the rule number 3, okay, the power equal to the potential energy and time. Okay, so in the short, if I write like this, okay, the power is equal to the work over time, and the second is the power is equal to the kinetic energy, okay, divided by the time. and this is the power is equal to the potential energy, the U, okay, the potential energy U, and the time. So these are the formulas, okay, we are using for the power. And yeah, yeah, one thing, actually there are basically the two units, okay, mostly we are using, okay. The one is the watt, okay. The watt and the joule per second, same meaning, okay. So if I say the watt, and this is the joule per second, same meaning. And there is a one more unit, this okay, this is a SI unit. This is the SI unit, okay, for the power. But there is a one more unit, actually, that is known as a commercial unit, and this is known as a horsepower. This is known as a horsepower. This horsepower, this is the first unit, and this is the second unit, and this is a horsepower, okay, horsepower. And in the short form, we are writing 1 HP, or this is HP, okay, like this HP, or sometimes like small, the horse and the power, okay. Actually, the horsepower is not a standard unit. This is a commercial unit. Commercial means it is written on the motors, the machines, the ACs, the big equipment, okay, electrical equipment, big one on that. And okay, so we cannot calculate, okay, in the horsepower. So there is a relation between the horsepower and the watt, okay. So the one horsepower is equal to 746 watt. So if it is given horsepower, then we have to change, okay, into the watt. No. Okay, so we are moving to the question number 16. And what the question number 16, says, okay, a boy of mass 40 kilogram climbs a vertical rope, okay. So this is the mass of the child, okay, boy, and he is climbing a vertical, okay, rope. This is some kind of the distance, you can say, or some kind of, you can say, the height, okay. So this is given, okay. And in, okay, vertical rope 10 meter in length in 15-second time, this 15-second time. So this is the value of the time with the constant velocity. Now they are saying calculate the work done by the body. So here they are saying calculate the work done. And the second point is, what is the value of the power. So if I write, okay, what it is given to me, if I make a diagram, okay, so if I make a diagram, okay, what they are saying. So this is a kind of the rope, okay. This is a rope, and there is a boy, okay. So this is a, okay, this is a boy, and the okay, this is a boy, and the mass of the boy, is 40 kilogram, and this boy is moving, okay, this boy is moving, okay, along the rope upside. And they are saying the height of the rope, or okay, the height of the rope is 10 meters. So this is the height of the rope, and this is 10 meters. The height of the rope is 10 meters, it is given. And the boy is reaching up to here, okay. And they are saying this boy is taking a time, okay, like from bottom to the top of the rope is 15-second time. So the time taken by the boy is 15-second time. Now they are saying, now this values are given, okay. The value of the h is given, that is 10 meter, and the time is given, the given that is 15-second. Now they are saying find the work, okay. So as I told you, okay, in the part 1 and here also, uh, the work, okay. Now this I have to decide, okay. We have some rules for the, which it is only for the work, it is like that, okay. The form of the formula, it is only for the it is only for the work. and we know, okay, the work and the energy, any kind of energy, they have the same meaning. Okay, so here what I can do, I can use okay, some formula for the work if I feel okay. In the same way, if I feel, I can use the formula for the energy. Okay, so both are applicable, both are correct. So what is my planning here? I will use the formula for the potential and energy here. Okay, so they are asking what is the work done. Okay, so I'm not going to find the work. So here I am finding what is the value of the potential energy. Okay, once it is reaching up to here, so the rule for the potential energy is this mgh. So this rule, okay, so I am going to use now for the, okay, so for the first part, for the first part, they are actually they are saying what is work, they are saying like that. Okay, so here I'm not finding, I can use work also, okay, but this is easy for me, okay, to use the formula for the potential energy because they have the same meaning. And this is mgh, and the mass is 40 kilogram, and the g is 9.8, and the height is 10 meter. So the value, if I calculate, okay, this number, so this will be, okay, so this will be how much? This will be 3920. So this is 3920 joule. So this is the value of the work. Okay, this is the value of the work, or you can say this is the value of the potential energy. Sometimes I can show the potential energy, okay, potential energy by pa, or sometimes I can show by u. Okay, so they have the same meaning, they are not different, they are same only. Okay, so this is the value of the work or the energy. So this is the answer, okay, for the part 1. This is the answer for the part 1. And for the part 2, okay, for the part 2, we have to find the power. Okay, so for the power is equal to, there are so many formulas. Okay, the work over time, this rule. Okay, and the kinetic energy over time, this rule. Okay, and the potential energy over time, this rule. Okay, so I plan to use this, so I will use this one. So the P is equal to the potential energy by the time. So here the potential energy is 3920 joule, and the time is how much? 15 seconds. So here the time is 15 seconds. Okay, so if I divide this number, I will get the value 261.3. So the value of the power is 261.3 watt. So this is the answer for the part 2. Now we can move for the part. Okay, now we can move to the question number 17. And what the question number 17 says, this is almost like same idea. It is not different, but same idea only. Okay, so here the question number 17 says, a 1665 kilogram man runs up 20-meter high stairs at a constant speed. So there is a one man. Okay, so like the stairs are like this, the stairs, this is stairs. So okay, so if I say this is the ground and this is the stairs going like this, and the man runs up. Okay, so if this is the man and man, and the mass of the man is 65 kilogram. So these are the stairs, and by using the stairs, the person is reaching up to here. The man is coming up to here. Now they are saying the stairs, these are 20-meter high. This is 20-meter high. So the height of the stair from the ground is 20-meter high. Okay. And if it takes 8 seconds to reach to the top, so the time taken by the man is 8 seconds. So this is the data given. Now they are asking what is the value of the power of the man. So, okay, so what given here? The mass of the man given, that is 65 kilogram, and the height given, this is 20 meter, and the time to reach to the top, it is given 8 seconds. Now they are asking the power. Okay, so the formula for the power is, okay, so there are three rules. Okay, so here I will use the rule, okay, the potential energy divided by the time, because I have this height here. Okay, so the formula for the potential energy is, this is mgh, the potential energy formula, and the time here, and the mass is 65, then the value of the g is 9.8, and the value of the height is 20, and they are saying the time is 8 seconds. So this is the number, and if I calculate the number, this will come 1592, 1592.5 in the unit of the watt. So this is the value of the power, okay, for the part 2. This is the answer for the part 2. Okay, this also has the same idea, okay, what I told okay, in the last questions, almost same. This is also the same idea, okay, what it is, and that I told. Okay, this, okay, I can solve question number 20. The electric motor of the model train. Okay, the model train means a toy train, a very small train. Okay, this is a model train, very small. Okay, and escalates the train from rest. Okay, like the velocity, okay, is 0. Okay, from rest to the 0 0.6, okay, 2 meter over second in this time. So this is, okay, the value of the final velocity, and this is the value of the time. Okay, 21 milli, but here the time is millisecond, and the total mass of the train is 875 grams. This is very small. It is a toy train. So okay, so if I make a small diagram, so this is the, okay, say ground, and on the ground this is the train. Okay, so this is the train, and the mass of the train, okay, the what it is given here, the mass of the train is 875. Okay, 875 gram, but gram you cannot use. Okay, so you have to convert this gram into kilogram. So this is 0.875, and this is in kilogram, like that. And this train started from rest. Okay, so this is 0, and this is 0, and the train is moving from here to here, and the train is reaching, okay, up to here, and the velocity is given. Okay, so this I can say is the final velocity, and the velocity is given, that is 0.62 meter meter over second. Okay, like from here to here, and from this point, okay, to this point, the train has taken a time, okay, taken a time of 21 millisecond. Okay, so millisecond you cannot use, so you need to change the milli. This is milli, okay, and you need to change milli, that is 10 to the power minus 3. So this is 10 to the power minus 3, and so this will be in second. So the time is given here, and now they are saying, okay, the power delivered to the train. Now, okay, so here we have to find the power. Okay, we have to find the power. So I have the three rules, okay, to find the power. And because I have some, okay, I have some velocity values, okay, and I have some time, okay, so I'm planning to use the power equal to the kinetic energy, okay, divided by time. Okay, so it is, sometimes actually here I am not using. Sometimes we can do like that. Okay, for the simplicity, there is no change in the answer. Okay, actually in the problem, this is one velocity given. Okay, and this is other velocity given. So here there are two velocities. Okay, and here this is 0. Okay, so if I'm not taking, okay, if I'm not considering, okay, this the vi, okay, so it will not affect my answer. Okay, and the problem will be easier here, okay, in this case. So okay, so you can say there is only one velocity. Okay, so don't say like final, this is v, I can say. So the power is equal to the kinetic energy over time, and the kinetic energy is the half mass of the train and the velocity power 2, and this is the time. And so this half, the half I can write like this, easy for me. Okay, 0 0.5, and the mass of the train, okay, mass of the train is this mass. Okay, the mass of the train is 0.875 kilogram, and the velocity, okay, of the train. Okay, so here I'm using only one, not like vf and the vi, only it will work. Okay, because the other, if it is not zero, then we have to use two. For example, if this is not zero, if they say the velocity is, okay, say 2 meters, something like this, then we cannot ignore. Here we can ignore because it is zero, that's why, otherwise no. So this is 0.62, and this is power 2, and the time here is 21 millisecond. So this is 21 multiplied by 10 to the power minus 3. So the whole thing, okay, I have to calculate, and if I calculate this thing, okay, so if I calculate on the paper, this will be, okay, this will be 8 watt. This will be 8 watt. Okay, so the power of the train is 8 watt. The power of the train is 8 watt. This is your answer. Okay, this is one problem. Okay, you can try this problem. Okay, this question already I solved. Okay, so the chapter is finished.